not too hard. The concept we're studying is iterated integrals, and that means taking several integrals in a row. One slight difficulty that we have with iterated integrals, or just with integrals in multivariable, is the fact that we have partial derivatives, and if we're looking for the actual functions, we won't just have a constant like in one variable calculus. Let's see what I mean by this. So if f, the first partial derivative, f sub x of xy is 2xy, then when we integrate, we would quite naturally find that this is x squared times y, but then instead of just having a plus c, c being a number, it could be any function of y. Because let's say we had x squared y plus sine y, then the first partial derivative in terms of x, differentiating in terms of x, would make this entire term disappear. So let's have a first example of an integral. This time we see that the variable of integration is y, so always pay attention to the information here, and the boundaries are y equals 1 and y equals x. So if we integrate, we get negative 2x squared times y to the negative 1, plus the integral of 2y is y squared, and we integrate from 1 to x. You can write it with a bar like that. If there's no confusion possible, that's great. If it helps, for clarity's sake, you can put brackets like this and leave your limits of integration like that. So if I substitute y equals x and then minus substituting y equals 1, I get negative 2x plus x squared minus negative 2x squared plus 1. And putting like terms together, we find 3x squared minus 2x minus 1. So I didn't need to put a plus c here. Just like in one variable calculus, this would cancel out. I would have a plus c here, a minus c here, and they would disappear. An iterated integral is a series of integrals that are performed consecutively. So here's an example. What's important is to understand the order. It's like you had a big parenthesis here. So this dy goes with these boundaries, y equals 1 to y equals x. And then once we've performed that, we have an integral in terms of x that goes from x equals 1 to x equals 2. So when we integrate, we can actually leave the outside as it is and focus on the parenthesis here. What's the integral of x squared in terms of y? It's x squared times y. X squared should be considered a constant. And then negative 4xy, if we integrate that, we will get negative 2x y squared. And all of this is integrated from y equals 1 to y equals x. So I'll just leave this like that. Substitute x. So y equals x, x cubed minus 2x cubed, and then I substitute y equals 1, so x squared minus 2x. Before integrating in terms of x, I'll put like terms together. So x cubed minus 2x cubed, we have negative x cubed minus x squared plus 2x dx. From x equals 1 to x equals 2. That becomes negative 1 over 4x power 4 minus 1 over 3x cubed plus x squared from 1 to 2, and if you plug in x equals 2, x equals 1, and you subtract, what you get is negative 37 over 12. I'm skipping here the part where we just substitute x equals 1 and x equals 2. Okay, moving on. As we saw in the previous example, the inside limit of integration can contain the outer variable, but the outer limits must be constant with respect to all variables of integration. It doesn't mean you cannot have any other letters, but you can't have, you couldn't have a y in the outer integration that we just did. So regions that can be defined as in the note above are called y-simple or vertically simple. We're going to prefer vertically simple if x is the outside variable. So an example of a y-simple region would be like that, because vertically it's always easy to define. Y goes from here to there, y goes from here to there. And regions that can be defined as in the note above are called x-simple or horizontally simple if y is the outside variable. So here, this example here is not x-simple because it's really hard to integrate horizontally. We would have to go from here to there and then jump and then from here to there again. So this is y-simple. It's not x-simple. Actually, these two terms are really not so important. What's important is that we figure out when we have a region of integration, what should we pick for the inside and what should we pick for the outside variable of integration. And it's going to come down to logic. So the region of integration we often call it R, is the region determined by the intervals defined by the limits of integration. Here are two examples where we want to see what the region of integration are. In these examples, it really does not matter what the function is. We just are curious about, in the xy plane, what is the shape of the region where y goes from 1 to x and x goes from 1 to 2. So let's see. So we have the xy plane, and we can focus on the limits for the variable x. So they are x equals 1 and x equals 2. So x goes from 1 to 2. What about y? Y goes from y equals 1 to y equals x. So y equals 1 is like this, and y equals x is a graph like that, is a line like that. So when we have all this information, we can probably deduce where the region is. It's the region where x goes from 1 to 2 and y goes from 1 to x. So it's this triangle here. Let's do another example. So we'll start with the outer variable first. Y goes from 0 to 2. That's easy. Y equals 0, y equals 2. And then how does x behave? X goes from y squared to 4. So x equals y squared is a horizontal parabola. like this, and it goes from x equals y squared to x equals 4, so 1, 2, 3, 4, like this. So let's think again. Y goes from 0 to 2, and x goes from y squared to 4. So we need to be careful. It could be this region. It could also be this one. You have to think a little bit. So it goes from x equals y squared, which is this curve, to x equals 4. And we conclude that this is the region where we are integrating. What is the function we're integrating here? It seems to be just f of x and y equals 1. Here, f of x and y was equal to x squared minus 4xy. We can just have 1. So if we're looking for the area of a region in the plane, we do exactly that. We set up f of xy equals 1 here, and the area is simply found by integrating from x from a to b, and then y from the function below to the function above. And similarly, if we have a function that is, let me see, I feel like this should say y simple, and this should say x simple. I hope I'm not, yes. It doesn't matter. The terms don't matter as long as you can find an integral. So how do we prove that? This is very short. It's going to immediately get down to what we know from regular calculus. So if we are if we only prove the first one, we want to show, sorry, d1 of x, d2 of x. So we're interested in finding the area between these two graphs from g1 of x to g2 of x. And it is said that this is the integral from a to b of the integral from g1 to g2 of dy dx. We can show this very quickly. This is 1, so if we integrate, we get y integrated from g1 of x to g2 of x. And later we would integrate in terms of x. And now using the fundamental theorem of calculus, this is the integral from a to b of g2 of x minus g1 of x dx. So we fall back on the usual definition. If we want the area between two curves, we do the integral of the top one minus the bottom one. So it's very easy. This equation here is just going to be the equation for any area, the general equation. We don't want to write it like that. Just in general, it's like that. And this is much easier to expand than if we're looking for volumes. It's going to be a triple integral with dz dy dx. 1 time dz dy dx. So find the area of the region bounded by the graphs of f of x equals sine x and g of x equals cosine x. This is something you can obviously do using AP Calc AB material, but if we want to try and use the new definition, then the area is the integral from pi over 4 to 5 pi over 4 of the integral from cosine x to sine x dy dx. So remember, for the inside integral, it's okay to have outside variables, but I would not be allowed to have a y in the limits of integration here. So when I integrate this, I get y. It's the integral of 1 times dy, so it's y. And when I substitute, instantly it gives us, we fall back on the definition from AP Calculus AB. And now if we integrate this, we get negative cosine x minus sine x from pi over 4 to 5 pi over 4. And if we substitute, it is negative root 2 over 2 minus negative root 2 over 2 minus negative root 2 over 2 minus root 2 over 2. And all of this is equal to 2 root 2. Let me just bring the blind down. So the example here will require us to understand a little bit what the area of the region, or what the region of integration is. So let's make a sketch to find out what we're talking about. We have x equals 0, which is here. We have x equals y squared minus y plus 1, which looks sort of like this. X equals y squared minus y plus 1. We have y equals 0, and we have y equals 2. So the region that is bounded by y equals 0, x equals 0, y equals 2, and x equals y squared minus y plus 1 is here. And the best choice, since this is a horizontally simple region, is going to be to integrate. So a equals, and we're going to integrate dx dy. So y goes from 0 to 2, and x goes from 0 to y squared minus y plus 1. So if we integrate this, it's x from y squared minus y plus 1 to 0, so it becomes y squared minus y plus 1 dy. And if we integrate this, 1/3 y cubed minus 1/2 y squared plus y from 0 to 2. And if we substitute 8 over 3 minus 2 plus 2 minus 0. So altogether we find that it's 8 over 3. Lastly, for this section, a little exercise that will come in handy sometimes. It's to try to switch the order of operation. So here, the order of integration, sorry. Here, the integral we are given tells us dy dx. But if you look at this function, it's actually not possible to integrate 4e to the y squared. However, we can use the trick of drawing the region and then trying to rewrite an integral that will have dx dy. Let's see how this works. It's going to be useful in also with 3 variables, dy, dx, dz. So what we know is that x goes from 0 to 1, so x equals 0, x equals 1, and then y goes from y equals 2x to y equals 2. So y equals 2x, and then y equals 2, in fact, goes exactly through the intersection here. So what region are we talking about? X goes from 0 to 1, y goes from 2x to 2, so it is this region. So I can rewrite this expression here as an integral 4e to the y squared doesn't change, but I want to express this region differently with dx dy instead of dy dx. So let's look at y. Y goes from 0 to 2. Y goes from 0 to 2. And then x goes from 0 to this. So x goes from 0, and this line here in terms of x is 1/2 y. So from 0 to 1/2 y. I hope this makes sense. This is certainly the hardest thing in this section. Now that we've flipped the order of integration, we get a case where we actually can integrate. This is the integral from 0 to 2 dy. Let's see what happens in the middle. This is x times 4e to the y squared. Integrated from 0 to 1/2 y, which is so x equals 1/2 y, so it becomes 2ye to the y squared dy. If we substitute 0, we'll just get 0. And now this, it's possible to integrate. We can make a substitution. So for example, u equals y squared, and in that case du equals 2y dy. So conveniently, this is equal to du, and e to the y squared equals e power u. Integral of e power u du. Remember that you have to be careful with your limits of integration. Y equals 0, y equals 2. So we now have u equals 0, u equals 4, because we use u equals y squared. U equals 0, u equals 4. Here it was y equals 0, y equals 2. So the integral of e to the u du is e to the u, integrated from 0 to 4, and we find e to the 4 minus 1. So as we see in this example, sometimes one order of integration doesn't work, but the other one works. Okay, I hope this was okay enough for you to understand this section. Thank you very much. I'll see you next week.